So Carmen asked me, how long have I known David? And I think it's been 45 years practically, so it's been a while. Anyway, this is David Epstein from Warwick, who is, I tried to explain to her that when I started doing topology 45 years ago, I knew the names of all the people doing topology in the United Kingdom, starting with Christopher Zeeman, David Epstein, and other people. But I said he knew all the ones at Warwick. And David was, I think he said he was there even before Christopher Zeeman. That's really a founder member of the topology team. And so I'm very happy that he's back. And he will talk to us about machine learning and topology.
Okay, well, thank you very much for inviting me to speak. And I'm really pleased about it. I'm not so sure you'll be pleased to hear what I have to say. So I'll start off by saying that I'm actually a kind of imposter in giving this talk because it's not in my area, and it's in an area where it's a very popular area at the moment, and there are thousands of papers written, and I must confess that I don't know the literature in the area. I've just started trying to do things in it, and I mean, it's quite probable that everything I say is already well known to people. Maybe to people sitting in this room, what I have to say is already well known. But
they wouldn't have come here.
I'm presenting
it already.
Presenting the ideas I had when chatting to students at Warwick who are dealing with, who are computer scientists, but dealing with this sort of data flood that we're experiencing in science. So the hope is that this kind of investigation will apply to real data. But at present, we're just using synthetic data. I mean, I'm using synthetic data. Now, I mean, the point is, so you have some sort of large quantity of data here, and you might have ideas for algorithms to make this data intelligible. And how do you know that the data, how do you know that your algorithms so you have some very questionable data to make your data intelligible. So the question is, how do you know whether your algorithms are doing what you think they're doing? And that's why we have synthetic data. So this is data which the writer, which the person who produces the algorithms, tries the algorithms out on. And here you know the facts, and you know what you're trying to achieve with the algorithms. So if the algorithms do the correct thing on the synthetic data, then you have a vague chance of being successful with the real data. If, on the other hand, as so often happens, the algorithms do not achieve what you want them to, what you think they ought to achieve on the synthetic data, then they have no chance at all on the real data. Actually, there are many people, I know very famous people, who tell me that they only work with synthetic data because real data is too difficult. But the objective is to have things work on real data. And so I mean, suppose you are collecting data of some sort. I mean, you might be a sociologist collecting hundreds of different items of data about a large population of people, or you might be a scientist collecting biological data, many different things. A particular example that comes up very often is if you have an image. So a typical image might be 1,000 by 1,000 pixels. And even in a black and white picture, that gives you 10 to the 6 bits of data. And modern imaging is getting bigger and bigger and bigger. I mean, they're now biologists, medical doctors studying molecular phenomena in medicine have images which are vastly larger than that, and this is the kind of thing that we have to cope with. So this is why we need these kind of algorithms. So now, when you've got, so suppose you just, so for each item, whatever you're measuring, you have 100 measurements. Then that gives data in 100-dimensional space. But human beings tend to, are only kind of, evolution has made us so that we only can grasp things in 3 dimensions, or actually 3 dimensions. That's very hard, but preferably 2 dimensions. So, if you start with data in 100-dimensional space, then you want to reduce dimensions somehow to some low-dimensional space. So you take your, whatever, you've got a point cloud in 100-dimensional space from this kind of data. And in order to make it comprehensible to the human mind, you want to reduce the dimension to a dimension where you can really kind of understand what's going on. And what I want to talk about is a particular kind of dimension reduction. So, so I'm supposing, so maybe, so possibly this is, so possibly this data is clusters around some low-dimensional manifold. Low-dimensional submanifold of 100-dimensional space. And then, so you've got something. So a submanifold, that just means a space that's locally like, if you look at just a little piece of it, it's like a manifold. So, I mean, for example, you might have a curve, a one-dimensional curve in high-dimensional space, and the data is clustered around this, so that the data that you actually see is like that. Actually, this is very sort of, all this is quite problematic. There's, I won't talk about the problems. I'll just show you what I've done, which is not. So let me perhaps make a simpler example. I mean, I don't know if you remember, I'm not sure what I learned as Boyle's law, or a sort of advanced form of Boyle's law, which is the pressure times the volume equals the number of moles times, that's a kind of just a measure of quantity of the gas, the number of moles times the absolute temperature times a constant. So you have four variables, so you four-dimensional space with coordinates p, v, moles, and temperature. And now, I mean, suppose suppose what you did. I mean, this is not what scientists actually did, but suppose what you do is you do thousands of experiments where you measure these four variables and you keep on changing everything. And then, so in your four-dimensional space, you'll get a cloud of points. And since measurements in physics are never precise, these will cluster around the three-dimensional submanifold, namely the set of points PVMT which satisfy this equation. I mean, this is a universal constant, which I was looking up in Google just before this lecture, but I've forgotten what it is. So this is, if you did that experiment in physics, then you would get, each time you did the experiment, you would get 1 point in four-dimensional space, one collection of four numbers, and then, but because of Boyle's law, they would cluster around there. So if you were capable of extracting a three-dimensional manifold from this four-dimensional cloud, then you would extract Boyle's law. In fact, this law was discovered, I mean, theoretically by, I think the original Boyle's law, pressure times volume as a constant, was discovered in the kind of way I've just said, going from 2 dimensions down to 1, with keeping this, the temperature and the quantity of gas constant. But the full law was discovered by, from the theory of gas dynamics. And this result comes out of the theory and has then subsequently been verified by experiment. So now I want to show you, I've taken the very, very simplest example possible, well, not quite, almost the simplest possible situation, to show you how my scheme for trying to recover the submanifold. So the objective is to start with data and end with the submanifold. Of course, this is only possible if your data really is data clustered around the submanifold, which may or may not be the case. But if it is clustered around, then what kind of means can you use to recover the submanifold? Okay, so let me see if I can recover my so this is the University of Edinburgh.
Without
You said you don't want to be online.
How do I?
You close it.
Okay, so this is a MATLAB program which I wrote over the last few days, and it's got random input of a certain kind. I mean, it's controlled random, so I'm, to some extent, I'm the hostage of fortune. This could go entirely wrong. In fact, there's a certain probability, which I hope is a small probability, that this will, a true probability that this experiment will go completely wrong, because when you're doing things randomly, things can go wrong. Anyway, so the way this MATLAB program works is that the double percentage signs sort of cut the program up into kind of paragraphs, and you can run them one at a time, which is what I'm going to do, and hope that I don't make a complete fool of MATLAB. So let's see. So the first thing is to show that, so as I said, this is synthetic data, and this is going to be the submanifold. The semicircle is going to be the submanifold that I want to recover. So it's a really simple situation. The submanifold I want to recover is only one-dimensional. Then the next thing I do is to create, just choose a number of points up here at random, and the number of points I've chosen 200 points at random on this semicircle. And every time you run it, it will choose different points. So these red dots, they're rather large, so they seem to fill up the whole space. But you can see anyway, there are gaps. The next thing I do is to add to each one of these red points, I add a Gaussian, so that's also random. And there are these blue points. Each one of these blue points is sort of associated with a single one of these red points, and it's so it's just, I mean, it's the convolution of the measure on this. You sample, I mean, in mathematical terms, which I'm not sure you're wise to use, but anyway, in mathematical terms, you've got the uniform measure on the semicircle, and it's convolved with a Gaussian. And then you sample from that convolved and you get that. So I think the next thing I do is I remove everything except, so this is the synthetic data that I want to start with, and from that I want to recover the semicircle. I mean, anyone who wants this program, I'm happy to send it to them. It's not particularly secret, as I say. It's almost certainly the same kind of thing that's been done many times. So what am I going to do now? Well, we're trying to recover from the set of points a space, namely the semicircle. And so the first thing I want to do is to transform this into a space. And the way that I'm going to do it is I'll take the two nearest points, which might be these two, for example, up there, and maybe I should use a pointer. But anyway, I start with two nearby points. The nearest two and I make an edge there. But then I just carry on joining whatever 2 points are nearest each other that have not already been joined. And I stop as soon as all the points have been joined into one component. So I just think of these are the initial components, and you join, if you need, you join 2 of them, those 2 fall into the same component. So all the components get bigger and bigger, and I stop immediately, the whole thing forms one component. So, oh dear, I've done the wrong thing. Sorry. You have to watch out where you click. I think I'd better just quickly start from the beginning again, otherwise. So what this is just the result of the process that I've just said, adding on the shortest edge that's not yet filled in, one at a time until you get a single component. And then this big red dot there is just a random one of these points. That I just chose one of them at random. And then the next thing I do is I choose the furthest point from that, which is probably going to be down there, and I choose the nearest point, the furthest point from that, which is down there, and the furthest point then from that, which is way over there.
Short question.
Yeah,
Do you
just
measure?
hang on, just let me, I'll be with you in a second. Yeah, sorry.
So do you measure distance now by hops or by the lengths?
It's
of
by the Euclidean length.
summing up the Euclidean length?
Yeah.
Okay.
I mean, because the sort of idea behind it is it's supposed in some way to think of real data, like PV equals moles times T times a constant. And each of the terms, PV, T, and number of moles, you're measuring with an error. So I've modelled that with a Gaussian error. And then, yeah, I mean, there are questions you can ask, like, you know, if you change the units in which you're measuring pressure, then you're scaling the thing in one direction, and that changes the distance. Well, I'm just not bothering about that for the moment, but it is a question. I mean, one thing you can do, which is often done in statistics, is each of your measurements you can scale. So here's one approach in statistics for each measurement, or way of measuring. I don't know how to explain this. So each coordinate, I mean, it's about for e.g. pressure in these experiments. What you do is you change scale linearly so that the mean equals 0 and the standard deviation equals 1. So that statisticians frequently do that. I mean, that's also potentially problematic because, I mean, suppose you were to add something that has absolutely nothing to do with the experiment, like the distance between the sun and the moon on the day you're doing this. pressure, then that would be a kind of completely random and uncorrelated with the other thing, and then standardizing it like that would hardly make sense. Or I mean, you might be measuring something that's constant, and the variations in this constant thing that you measure might be absolutely minute. And then what that process does is it magnifies these minute and totally inconsequential errors to have standard deviation 1. But anyway, I mean, it is a problem as to what to do, and you usually need to actually look at the kind of data you're dealing with in order to make sense of it. Okay, so let me carry on with that. Doing the right.
Can I ask, how do you check the number of components?
Sorry?
How do you check that there's only one component?
Let's see, it's in the code, but it's in a previous chunk. I mean, all that I do is, I mean, technically, I use an algorithm due to Tarjan, and which is called merge find, which is an incredibly fast program. And this is a program where you have a set partitioned into disjoint chunks, and which are here, in this case, the components. And there are two operations you can do. You can merge two chunks into a single chunk, or you can find the name of a chunk. I mean, each chunk is named, and when you merge to it, inherits one of the two names. And so I use that, Tarjan union find, and so that it's very quick in order to, I mean, you see, this just does in a flash, and so it's very. So every time I do a merge operation, I just reduce the number of components by 1. I start off with every point being a separate component, and then I count down until the number reaches 1, and then I stop. So that's the process that I mentioned. From this random point, I first find the furthest point, which is either that point or that point. And then, from whatever the furthest point is, I then find the furthest point from that. And actually, because there's some strange situations sometimes, I repeat the process until I get actually what's called the diameter of the graph, the distance between, the furthest distance between any 2 points in the graph. Right, and I use, I don't know if you're a computer scientist, I use Dijkstra's algorithm, if I've got the pronunciation correct, to get the distance, which is a rather slow algorithm, but to get the distance from a point, if you fix a point, it gives you works out the distance to every other point. So it's something, these programs are provided in MATLAB. I had to write out Tarjan's algorithm myself, but I didn't write out Dijkstra's algorithm. It's provided as part of MATLAB. But I won't try and go back because I'll probably click on the wrong thing and get it mixed up again. We can go to it later if you want to ask. So now what I have is a long path, And I use this path in order to kind of, I want to associate, here I've got this one-dimensional in a second, I think it may be a screen later or something, I'll show you why. I mean, there's the question which I've skipped over as to, you start with this cloud of points, and how do I decide that it's one-dimensional? I've skipped over that. But anyway, you get this in this longest path. Let me carry on.
If it had been a circle, not a semicircle, what would you now have?
Sorry?
If it had been a circle, not a semicircle, what would you now have?
Oh, I would have, yeah, I mean, I'm cheating a bit. I would have had to do something slightly more complicated,
Okay.
but I was preparing the lecture under time pressure.
Okay,
So,
okay, fine.
but yeah, I mean, you do have to do something, and I've also skipped over the question of number of components. I mean, if you know, I mean, your initial curve in this high dimensional space could be, and so really I should be more careful when I start combining things. I mean, I thought about doing this, but I was just under too much time pressure. I mean, you should really see, when you have to do a really long hop to go from one to the other, you should maybe say to yourself that these are separate components. Or you should do some other kind of clustering before starting on, I mean, there are many different algorithms for clustering in statistics and statistical computer science. And these might, if you chose the correct algorithm, would say that these three sets of random points formed a separate cluster. I haven't done that, but one could think every time before adding another edge, whether that edge is kind of suddenly much longer than the other edges, and decide to treat the separate components, the different components at that point differently.
But that would depend on the density from which you're sampling, right? Because if you had
yeah.
a lot of noise,
Yeah.
then you would have a problem in deciding whether this is a separate component.
Yeah, yeah, it's not, yeah, there are lots of things that could go wrong. I mean, I mean, what's lacking in all this, what I've done, is some theorems that say, under the following circumstances, you have such and such a probability that this process will work. And I haven't done that kind of analysis at all. Yeah, so, I mean, we could try later putting in smaller values of n and see what happens. Right, so, right, so I was going to say, talk about, I mean, I've been saying this is one-dimensional. I mean, we know it's one-dimensional because we started with a semicircle. But we didn't really start with a semicircle. We started, I mean, we're supposed to put ourselves in the frame of mind that we started with a random cloud of points. So how do you know that this is one-dimensional? Well, I know of two approaches, and there are probably many others. The approach that I use, one approach that I'm suggesting is that. Now, so what exactly is that approach? So I want to determine the dimension. I've got my cloud of points. So I've started with this cloud, and I've made a space of this one-dimensional complex. And that, the one-dimensional complex, enables me to, I mean, once I've put in these edges, then that gives me a way of getting hold of the distance from any point to any other point. And so suppose your space is k-dimensional, then we'll ignore for the moment questions of curvature. Then you get something like the number of points at this, so fix a point, and what's the dimension around that point. Now count the number of other points. I'll fix a point, call it P, with the distance, points X, with the distance of P to X less than or equal to R. So I'll call this f of R. F of R is the number of points X, distance from P. So this is some kind of random point. In fact, yeah. And now we expect f of R to be something like constant times R to the K. I mean, that's true in Euclidean space. So what we actually expect is, if we do the graph, we expect some funny behavior here at the beginning. This is R, and this is f of R. And then we expect over a certain region where curvature doesn't count, where this is something like a constant times R to the K. And then at the end, we expect some other funny behavior. So what I actually did was to graph the log of R against the log of f of R. and then when you take logs here, so you get log of f of R, it would be something like the log of the constant plus k times the log of R. So this should be linear with slope k equals the dimension. So that's what I did here. And yeah, these axes, I mean, because MATLAB cuts these intervals on the x-axis into half units, and the unit 1 in the y direction, so there's an optical illusion that makes that distance. But maybe it's the way I've got the display on, which I don't understand. I mean, that distance is supposed to be the same as that distance. Maybe it's not. Anyway, that's what I was trying to achieve. And then you look at the slope, and you have this funny business at the beginning, and then the slope, roughly 1. So you can read off the slope. I mean, this, you see that if we're assuming it's a manifold, and if it's a manifold of dimension k, then the linear part, the slope, is bound to be an integer. So it's not just an arbitrary slope, it's an integer slope. And so you can sort of look for the nearest integer that matches. And you get 1. I mean, the other way is, I don't know whether you have any lectures on it here in the algebraic topology, or maybe you had a thing. I mean, you can also get it from something called persistence homology.
it's cropped
I
up.
won't bother to explain that, but the two different, so these are two different ways that you can estimate the sort of dimension of the space. And I mean, this is a simple-minded way. Logging this is a simple-minded way, which gives the slope properly on many different, it gives the dimension of what you actually, in the synthetic data of the thing you started out with pretty well. So, actually, no, I didn't want to cover that. So now we've got this red thing, which is this rough path. There at the top there, I had it printed out. You probably didn't notice it happening, but it happened after I did, I think, 2 clicks ago. So the first thing is the length of this red curve, and the second is pi itself. I mean, if you were 100% accurate at this point, these two numbers would be the same. So this actually is longer than it should be, because you've got some, your random points are way out there, and you've got some sharp turns as well, and it's shorter because it tends to occupy the inner radius, the inner part of this rather than the outer one. But anyway, that gives that sort of, well, when I found that, I had some confidence that I was on the right track, because these numbers are not too far apart. So the purpose of this is to give a one-dimensional parameter, t, which you can use to kind of specify how far around in this graph every single point is. And so the next thing I do is to take this point, so I sort of parameterize this red curve from 0 up to 3.4965, and if I want to know the parameter of this point, I project this, I'll take the nearest point on this red curve to that point, and I think I should have set some parameter on there. Told my computer not to shut down so quickly. But I don't think I'll bother to try to do that now. So for every point there, you take the nearest point there, and so every point on this graph gets a parameter along a number along this red curve, somewhere between 0 and 3.4965, including the endpoints. So it arranges these points in order. And now the next step is to take a spline based on the parameter. You have the parameter there, and you have the point out there, and you compute a spline with least squares for all. You take all these points, every single one of these points into account, and you try and minimize the distance between the spline curve and each of those vertices, using trying to minimize the sum of squares of the distance. And here it's drawn, this spline curve is this green curve that's been drawn in there. And now I'll get rid of all the dross so that you, and now the next step is to bring back the original curve that we started with, that produced, from which I've got all this data, and compare it with this, our attempt to recover the curve. And that's the result we get. So this green thing is coming from splines, and maybe I should stop and say a little bit about what splines are. But the point about this red curve that I had is that you need some kind of basic parameter that things are functions of in order to find your best possible curve. I mean, let's see, it's 4 minutes.
You start at 10 past anyway.
10 past.
So you don't even.
So I should say something about what splines are, which again, like everything else in this talk, is something I don't fully understand, but I'm learning what amazing things splines are. Are there any experts on splines in the audience? So I hope I won't mislead you. But I mean, these splines are things. I mean, when you have drawing programs, if you've ever used a drawing program, you could tell it you want to make these points, you want to have a curve passing through these points, and it draws a smooth curve like that. And you can also, I mean, there are lots and lots of different spline programs. You can specify tangent directions at certain points and get it to go through that point with that tangent. And these are based on, I mean, you could have a large number of points here. And what's going on here is that there's some kind of space outside the space which is not shown in the drawing programs. And in my analysis, this outside space, this was provided. I should draw it in red because that outside space is provided by this. I mean, that was this red curve that's essential to the construction. But it doesn't really matter where you, I mean, there are lots of different ways you could divide it. And what the program does is, what a spline program does, it computes and these are usually they're two different cubics. I mean, there's the t, and there's x of t and y of t. And what's drawn is not the t direction at all, but it only shows x and y together. So I mean, you can get something which is not a function at all, because both x and y are functions of t, so you can get a parameterized thing. And in the spline thing, this so what it does is, for each chunk here, it computes a best cubic with certain properties, and the cubic's different there from there. So we've got different cubics. And these cubics only have the property that the first derivative are the same, or, well, point in the same direction, and the second derivatives match as well. And don't worry about anything else. They're just put together this thing in pieces. And the important thing to notice is that the absence of the T part in the actual final thing, which is why I was able to use a kind of funny curve without it doing any damage to the actual reconstruction. Anyway, this is a very huge theory. I mean, it's really important in industry, spline theory, and they use it for designing cars and the shapes of cars and aeroplane wings and God knows what. So they're massive papers, but they are either one dimensions in two or three or more dimensions. One in something is sort of comparatively easy, and it starts being difficult if you want a surface in a higher dimensional space. And the only thing, the papers all seem to be about 2 dimensions in 3, which is what's used in industry. Let's see, I wanted to quickly say the direction that I'm hoping to take in my work. Well, I'll put aside for the moment my training in pure mathematics and just trying to achieve results with synthetic data rather than prove theorems. What I would like to do is to have not one-dimensional data, but for trying to find 2-dimensional submanifolds, 3-dimensional submanifolds, and so on. So how do you do that? Well, instead of having doing the splines on this one-dimensional hidden T, you do this. You should do the splines on 2-dimensional things, and they're these standard functions that are used in spline theory, and a typical spline on here would be the sum of a constant. So let's say fi of x, gi of y. So, I mean, what they call them in spline theory tensor products. I suppose they are tensor products of spline functions in one dimension, but in less highfalutin language. You take sums of products of your known one-dimensional spline functions. These are often approximating cubics or other approximating functions. Multiply them together and add a whole lot of them, and then use that on a rectangle. So I haven't really gone into this, but the problem is that, you see, in one dimension, the pieces always fit together to form a manifold, but a nice sort of smooth manifold. But in 2 dimensions, I mean, your squares, if they fit together like that, that's fine, but you cannot make, say, a 2-sphere out of squares like that, I mean, it's sort of would contradict theorems in topology if you could. And instead you have to have sorry, that I'm not trying to draw a cube there. I'm trying to draw three sort of deformed squares. You have things like this with different numbers of squares meeting at a point in order to use the topology. So the fact that when you're doing splines, if these two are adjacent, these derivatives do not, the first derivatives, they're, I mean, the right-hand endpoint there and the left-hand endpoint there are the same point, go to the same point in the manifold, but the derivatives do not have to be equal. They only have to point in the same direction. So if you have x dash t on the right, y dash t does not have to be equal to x dash from the left, or the other thing, y dash t. It only has to be the same up to a constant in order to get a nice curve with a nice continuous tangent. And so what I would like to do, so this is future research, but what I would like to do is to first of all establish what the tangent space should be at a point, and then extending from that get reasonable tangent spaces over these lines there, and then extend that to reasonable tangent space, I mean an approximating tangent space over that square. And I'll just point out to you that it's a known theorem in topology that every differentiable manifold can be cut up into simplices. So, and now if you have a simplex, then strangely enough you can divide a simplex into squares as follows. I mean, it's just the, you just take the just use part of the what's called a barycentric subdivision. So if you take a 2 simplex, then it can be cut up into 3 squares. So these are not geometric squares, but they are, from the point of view of analysis, I mean, they diffeomorphic to actual squares. And you can use, so here you can use product splines. So I would try and get things right in some sense over the points first. Then I would like to try and get the approximations right over the ones, over the one-dimensional part. And then finally, over the two-dimensional part. And in that way, I'd construct a surface and some higher dimensional manifold that would be a good approximation to the original I started with. Okay, I've gone on longer than I wanted to because I wanted to, I mean, because we could, or you could come up afterwards, we could release people who need to be released. Because the point is that the program can be run choosing, you could change the parameters and you could see what happens. Or if you rerun it, if I run it again, I'll just quickly run it again.
Encore. Close that.
That is a stupid thing.
Close it. Yeah.
And now just run straight through from beginning to end. And there it produces that. So it's, I mean, see, it's not always by any means perfect, but that's the kind of variation you get. And the more points you start off with in your cloud, I'll run it again. The more points you start off with, the better the approximations, of course, but also the longer it takes. And in an actual experiment, you have to work with the actual data that's there. You can't just create more and more data at liberty. Anyway, I think I've gone on more than I should have, so I'll stop.
Thank you very much. Are there any questions?
In your code, you generated this red line before you knew that this thing was one dimension.
Yeah,
So-
no, but
Shouldn't you
Yeah.
first determine the dimension
Yeah,
and then
that's-
try to find some parameters based on this?
that's, yeah, I mean, well, so what would you, yeah, if you were faced with actual data, the first thing you'd have to do is various experiments to try and estimate the dimension. And the dimension of your point cloud might vary from place to place. And so you should try looking for the dimension around various points. I think this persistent homology idea, which I didn't explain, is quite useful, although I think the computations may be quite long. I haven't tried them. So the first thing to do, you have your space, and the next thing you do is get the dimension. Now, what would you do? So this is something like what one would do, or some variant of what I actually did, if you find that the space is one-dimensional, or you think it's one-dimensional. If it was two-dimensional, then what I would actually do is, so you have this two-dimensional, this cloud of surface, this cloud of points that you think is two-dimensional, and but you've connected it up so that you have all these edges connecting it. And what I would like to try and do is to place points fairly far apart. See, once you've done this, then you have a scale given to you, because, I mean, you can look at the lengths of the edges that you've had to add in. As you've been building this space with edges, then you have those lengths available to you, so you can use those as a kind of estimate of appropriate scale. And so what then, at quite a large factor times that scale, I would try and choose in this two-dimensional, sort of fuzzy two-dimensional cloud, I would try and choose points fairly far apart. I mean, I don't know, I suppose 5 times the maximum length of the edges I've added in. So I'll get these points all over the place. And you can keep on going until there's nowhere more. You can just plonk points down, but stop. Well, I mean, when you can't put an extra point down, less than 5 times your basic thing, you have to stop. So now you have a cloud of points. Now you have your two-dimensional, your kind of two-dimensional.
So you're trying to explain what to substitute for a diameter.
Yeah,
But you don't want to use the diameter, which is a one-dimensional thing.
that's right.
Yeah, it's a red line that you got by
Diameter.
running.
So we're trying to figure out what is the right
this.
notion in two-dimensional.
Yeah, that's exactly what I'm trying to do. So, so the idea is, I mean, my idea at the moment is to try and find sort of widely distributed points here. And I'd keep on putting in points until I can do no more. And then I would join them up. And then I would do something like the construction. I told you, making these into squares. And then I'll try and construct my splines on these squares. So that's, I could do the same kind of thing in many dimensions. Well, I don't know how well this would work, but I mean, I think maybe I'm going to need other ideas than the ones I've already had, but this seems to be a reasonable framework to try from. So that I should repeat my warning that this is a very intensively studied field, and this approach may not be at all the way it's going to be kind of tied up properly by mathematicians. The thing that is a crucial idea, which is this earth movers metric, well, which used in probability theory, which I think will play an important role. And there's a paper, important paper, but this subject has been contributed to by two different fields medalists, as far as I know, namely Charlie Fiffin and Steve Smale. And I haven't mastered their papers, so I mean that's something I should do fairly soon. But a lot of good people have written on this.
You mean the paper on testing the manifold hypothesis?
Sorry?
Steffman's collaboration with some theoretical computer scientists at MIT. Is this paper on testing the manifold hypothesis?
Yeah, that's Fiffman. Yeah,
Sorry.
yeah, that's right.
Using his Whitney extensions.
Yeah.
Right, which is some sort of fancy, way of thinking about splines and higher dimensions.
Yeah, I don't know. I must examine that paper. That's on my to-be-read list. Have you tried to read that paper?
No. But I know sort of a related problem that was inspired him, that the work that he did that made it is sort of knowledge relevant
Yeah.
for this.
Okay, any more questions? Thank you very much.